what I'm going to present you is a macrostructural analysis of deformed gabbros from a drill hole in the southwest Indian Ridge. So first of all, what are mid-ocean ridges? So they are divergent tectonic plate boundaries. It's the area where the oceanic crust is created by accretion of magmas coming from the mantle and crystallizing near the surface at the ridge axis. The area I'm studying is located in the southwest Indian Ridge, which is located here, and it's called the Atlantis Bank. It's a submarine massif which is located away from the ridge axis, which extension is, you can see it here, but it's north-south extension, and so it's 70 kilometers away from the ridge axis. And this is a really interesting area, and we will see why. So if you do a cross-section at the ridge axis, Earth cross-section, here you have the mantle in the bottom, and you have magma coming from the mantle crystallizing near the surface, and here you have crystallization of a gabbro pluton. And because we are in a special kind of ridge, a slow spreading ridge, the magmatic activity is not sufficient to accommodate the extension. So then we see development of some tectonic fault, a huge fault in blue here, which accommodate the extension and in the same time that exhumate the deep section of the oceanic crust and brought them to the surface. And so this kind of structure is exactly what corresponds to the Atlantis Bank. So the Atlantis Bank, this massif, corresponds to a plutonic gabbro that were in the deeper parts of the oceanic crust at the beginning. And in this massif, we have the opportunity to have a drill hole. And this is basically what I'm studying here, samples coming from the hole that have been drilled in this massif. And the aim is to study the ductile deformation of gabbros during their accretion at the ridge in order to better constrain the construction of magmatic gabbroic series at low spreading ridges. So I spoke about gabbros, but what is it exactly? So here you have a micro photograph with a PL for plagioclase, CPX for clinopyroxene, and OL for olivine. So you see it's mainly composed of plagioclase, a triclinic mineral, but you get also clinopyroxene, a monoclinic mineral, and olivine, an orthorhombic mineral. Here, the microphotograph, you see the magmatic microstructure, so undeformed microstructure. Speaking about microstructures, here is all the microstructures we can see in the hole, from not deformed microstructures to highly deformed ones. And let's see closely. So when the gabbros are not deformed, you have this nice microstructure with tabular hydral shape of plagioclase. And what we see is when deformation starts to occur in gabbros, the thing that happens is the recrystallization of plagioclase and only plagioclase. You see that there is no deformation at all in clinopyroxene or in olivine. And this is a porphyroclastic microstructure. Then, when deformation increases, we tend to have almost all of the plagioclase grains that are recrystallized, but we also have starting a recrystallization of clinopyroxenes and olivine from the edge of the grains to the core of the grains. A further increase in deformation leads to a marionettic microstructure where almost all of the grains are recrystallized, and we also see a decreasing of the grain size in average. as well as the development of a foliation in samples. And the last step is also a further decreasing of average grain size and an increase in development of the foliation we see in gabbros. So now, if we look at the distribution of the deformation and associated microstructures along the depths in the hole, you have in the y-axis the depths and the microstructures observed in the x-axis. You see that it's really heterogeneous, and we can have some areas here in the upper sections of the hole where in maybe 10 or 20 meter long and continuous areas we have a huge plastic foliation that have been developed, and we have proto-melanitic and porphyroclastic microstructures. And so we have a highly distributed deformation in long sections, and this is in contrast with what we see in the bottom of the hole, where deformation is much more localized, and you see the overall is slightly or undeformed, and sometimes we have some pulse of deformation leading to myelonitic to ultramyelonitic microstructures development. So now let's look at the EBSD analysis of these gabbros. And just before I begin, all the data, EBSD data I will show you are oriented with the downhole direction pointing toward the bottom. So all the maps and the pole figures are oriented this way because it is the only reference we have in the hole. So here we have a nice proto-melanitic olivine gabbros, a gabbros with much olivine into. And you see that plagioclase is a lot recrystallized as well as olivine, and we have associated CPOs that show point maximas in the pole figures. Here I show you the evolution of the J index calculated for 1 point per grain, 1 ppg. And you see first that there is no direct correlation in between the microstructure observed and the value of the J index. The second thing is that the J index here is from 0 to 5, and you see that in the upper parts it's mainly between 1 and 2, so it's very low. And then it's mainly between 1 and 3, slightly higher, but still very low. So now we are going to see at the association of the microstructures and the CPO patterns we can observe. So here you have a GAM map, a grain average misorientation map, showing that there is no deformation at all in grains. This is a magmatic undeformed microstructure, so it's okay with this. But what we see in the pole figures is that mainly in the O10 plane, we have a foliation. The trace of the foliation is the pink line here that has developed, unless even if it is not deformed. And this is totally normal, because when the gabbro is crystallizing at the ridge axis, it is in a dynamic environment, and this is this environment that creates this foliation plane development, but it's not associated to deformation. Here you have a orientation map of a porphyroclastic gabbro. All of the white areas are the other phases. It's not index points. It's only the plagioclase and olivine grains. So what we see here in this map is that we don't have a large spread in orientation in grains. If you look at in between porphyroclast and recrystallized grains, the range of color is quite reduced. And if we look at the CPO pattern, we see that the O10 plane still marks the CPO, the foliation plane, sorry, and that we have a girdle of orientation in this plane of the 100 axis. So now if we look only at porphyroclast in the same sample, so we see the mis-to-min map, which shows deformation into the porphyroclast, and here you see the small lines here are twins, and you see that deformation is not affected, at least by these twins. And so the CPO pattern we see here corresponds to the magmatic state, the previous, before deformation, sorry. And so we see again the 010 plane forming the foliation. And now in the same sample, if we look at recrystallized grains, we have again the same CPO pattern, so which is really which coincides with the little orientation spread we see in the orientation map. And now, if we look at the ultramelanitic gabbros, the most deformed ones, we see here the orientation map, and in the CPO we also see the 010 plane forming the foliation plane, but this time, sorry, we have development of a lineation on 100 axis, which is well visible here. So here it's a summary of all the CPO and associated microstructures from undeformed at the top to the highly deformed ones on the bottom. And what we see, so keep in mind that the downhole direction is toward the bottom. So all the variations you can see in the CPO in pole figures here are downhole variations. And so each time we have the 010 plane forming the foliation plane. You have the trace of the plane, remember here. And so we see that we have mostly planar structures for the less deformed gabbros. But when deformation increases in gabbros, then we tend to develop a lineation here in 100 axis. Now, if we represent the J-index and the associated microstructures in samples, we can see that when we reach proto-melanitic to ultra-melanitic microstructures, there is a strong decrease in the J-index values. And this is mainly an effect of recrystallization and maybe also of grain boundary activity, but this is something which is quite complicated to see directly within the EBSD. And another factor of this J-index decreasing while the deformation is increasing could be also the activation of different slip systems. Here you have a list of the main slip systems observed by transmission electron microscopy in plagioclase. And you see with the CPO patterns, here for example for this proto-melanitic gabbro, that the main slip planes corresponds to foliation plane, and also that the direction 100 corresponds to the lineation, which is, by the way, a Berger vector for the two main slip systems observed in plagioclase. And one other thing is that if you look here at the list, the main common one observed is the slip system with the 010 plane and the slip direction 001 that we don't see here in CPOs. But if you look at the misorientation rotation axis, if you plot it in an IPF, sorry, you can see that the maximum corresponds to the 100 axis, which by the way is the rotation, misorientation rotation axis associated to the 010 slip system. So it means that this slip system, which is the most commonly observed here, is active in samples, but is not a main one because we see a lot of misorientation which is still on the axis, corresponding to a dislocation density which is still here. So the SLIS system is not as active, sufficiently active to evacuate all the dislocations that are in the rotation misorientation axis. So to conclude about all of this, I show you that we have a pre-existing magmatic CPO giving a 010 foliation plane, and at the same time, when deformation occurs in gabbros, we have several subsystems active. Here I show you only 3, and the main active subsystems have the same slip plane as the foliation plane of the magmatic undeformed samples. And so the next step for me is to search for the other possibly active slip systems in order to investigate the influence of this pre-existing magmatic CPO on the possible activation of slip systems. Thank you.